Okay, analysis of variance. We're going to get back into analysis of variance, and we're going to take it a couple levels higher than what you've been exposed to already. Here you see the basic plan of analysis of variance in which you have two groups, and you're comparing two means. And you're going to answer the question, do the difference between the means occur by chance? This is also the problem of the t-test, as well as analysis of variance. And you can see at two-group level, two means, you have the same question, hypothesis testing for t-tests as well as analysis of variance. They're the same thing. Okay, now we're going to transition from the t-tests and two means to a situation in which you've got more than two means. You now have a set of means, and this set of means is stratified by the independent and dependent variables. So in this situation here, you've got 6 means. And the hypothesis is whether at least one of these means is significantly different than one of the other means, at least one. So you could have 3 means that are different from 3 other means, or 2 that are different from the others, or just one that's different from the others. But this technique allows you to test the hypothesis, test what the probability is for one mean, at least one mean being reliably different from at least one other mean. In this structured model of analysis of variance, the model is logically the same as simple ANOVA. So it's logically the same as what you've learned before. However, the variance components are conceptualized and calculated a little bit differently, but the logic is the same. It's easier in the structured model to handle unequal sample sizes. The structural model incorporates a deeper understanding of the logic of ANOVA, because now you're going to be dealing with multiple groups, and so you need to understand how you're contrasting them more clearly. And the structural model will help you understand more advanced ANOVA models, such as factorial ANOVA and multivariate analysis of variance and things like that. So there are advantages now to transitioning to including more than 2 means and beginning to conceptualize the variance contrast a little bit differently in a little more complex fashion. Structure model of the analysis of variance. The null hypothesis of ANOVA is that the several populations being compared all have the same mean. And that's the same hypothesis that was tested before, if they have the same mean. That's the null hypothesis. Now, testing this hypothesis that they have the same mean involves analyzing the variance in the study samples and understanding what variance is. So you should think to yourself, ponder, what is variance? What is variability in a study? Obviously, if all the subjects have the same scores, the variance would be small. The mean would equal the score of any subject. So the variability is very, very small. Now, if I'm testing the mean of populations, I need variability among those populations, within those populations, to contrast with the mean differences across the populations in order to find out what the probability is. By chance, you selected those samples from these populations. Would the means be different or would they be the same? And I calculate the probability for my study and test a hypothesis. The first step is to analyze what variance is and try to understand what variability is. Okay, now we're going to take an example where variance is described, and we're going to go into more detail about what variance means. The structural model presents variance as deviations, as differences. First, there's a deviation of a score, an individual subject score, from the grand mean. Remember, the grand mean is the average of all the subjects on the dependent measure. That's the grand mean. So the first is a deviation of an individual score from the grand mean. And this deviation has 2 parts to it. The deviation of the score from the sample mean that it comes from, and the deviation of the sample mean from the grand mean. And now we're going to examine this using a simple 3-group model that studies 3 different birth orders and how that influences or may or may not influence a dependent measure. But we're just using this as an example of how to calculate these deviations. The first step in this model is to download the file here. It's an Excel spreadsheet file, which I assume you all are familiar with. It's called birth order ANOVA.xls. So you need to go to the website for the course on Blackboard, and you should see a link there that's below the presentation. So there's a link for this presentation, and there should be a link there for this file. So download the file, it's very small, and open the file in Excel. And if you have Microsoft Office, you should have it. Okay, well, at any rate, you open the file in Excel, and it should look like this spreadsheet you see here. Now what we're going to do is go over this spreadsheet and talk about each element of variance that's in it. So you should have the spreadsheet open and this presentation open, and as we go through it, you should be able to look at the spreadsheet. You can kind of see things on this slide. They may not be as your spreadsheet. You can do either one as long as you can see the spreadsheet numbers. Okay, so here's the birth order example spreadsheet. And we're now going to calculate some of the deviation scores, which represent variance. Okay, so the first thing you should notice is you can compute the deviation of a score, say in cell B6, from the grand mean. You can also compute a deviation of the score, an individual score, say in cell B, indicates an individual subject, from the sample mean. And now we're going to compute the deviation of the sample mean from the grand mean. So now we've got these calculations, these subtractions we're doing. These are distances of an individual score from the different means that are part of the study. Okay, so score 9 minus the group mean of 7, the score there in B6 of 9, and the group mean is a value of 7, so that's the value of the first birth order group. And then we take the group mean score of 7 and subtract that from the grand mean, which is 5.58. So now we get 2, so 9 minus 7 is 2. 7 minus 5.58 is 1.42. We add those together and we get 3.42. That represents the deviation of the individual score from the grand mean. And that's the first measure of variance that we're going to calculate in analysis of variance, and then we'll partial this into its components, and I'll show you more in other examples here how we finally calculate the contrast to get our probability judgments. Okay, now we're going to add up these parts for all the subjects in the study. We're going to give them some special names. They're not going to be that unfamiliar to variance components that you've probably seen before. It's more how they're conceptualized and how they're partitioned that makes them different. It actually clarifies, I think, all of analysis of variance that we've studied so far. And even though it sounds like it's making things deeper and more complicated, it's actually clarifying and making things simpler, I think. Well, at any rate, we want to take all these deviations that we just did for that one subject and do them for all the subjects in the study. So if we take the square deviations, so we take the deviation of each score from the grand mean and square that. Then we add all those up for every subject in the study. We get the total sum of squares. Now this represents the distances of the individual scores from the grand mean in a form that's only in units that don't have any valence, don't have any positive or negative. They're just amounting to distance from the grand mean. Now you can imagine if you had a study in which there was no variability, all the subjects' scores would equal the grand mean. So if everybody scored, say, a 5 on this measure, the grand mean would be a 5, all the sample means would be a 5, and there'd be no variability. But now we don't have that situation, and in every study you have some variability, hopefully. If you don't have any variability, you can't do any statistics. So the total sum of squares is the sum of the square deviations of each score from the grand mean. The sum of squares within is the sum of the square deviations of the individual scores from their sample means. So that's the amount of deviation that's within the samples, that's within each group. Because you're measuring the distance from an individual score to its sample mean. And finally, the sum of squares between is the sum of square deviations of the sample means from the grand mean. So it's the number of deviations of the sample mean from the grand mean. And that represents the distance that the samples each other, if you think about it. If that's large, that means that the sample means are far from the grand mean. And that might suggest that if that number is big, it would probably suggest that there's a difference between means. And it may or may not be statistically significant. But if that's large, if that sum of squares between is large, that means the samples, or at least one of them, is far from the grand mean. And you see finally here that the total is equal to the sum of squares within plus the sum of squares between, which we stated before in another form. The deviation of a score from the grand mean is made up of the score's distance from its sample mean plus the sample mean's distance from the grand mean. And this is just another way of stating that in terms referred to as sum of squares within or between. Now we're going to move from sum of square deviations and that kind of language to estimations of variance in populations. Now remember, when you move from samples to generalized into populations, you need to correct for a bias that occurs in that generalization because you're going from a sample that's smaller number than the population. And you're going to be dividing the variance estimates by the degrees of freedom. Degrees of freedom is almost always 1 minus the sample size, or in this case also 1 minus the group number size. But that's going to be the divisor because we have a systematic bias in estimating from a population from a sample, and we have to correct for that to be a little more conservative. So here you see the variance between, or the mean squares between, is equal to the sum of squares between, which we calculated before, divided by the degrees of freedom between. And the degrees of freedom between is a number of groups, which is k, minus 1. So in this case we have 3 groups, so it's 3 minus 1 or 2. Now the variance within, or the mean squares within, is equal to the sum of squares within divided by the degrees of freedom within. Now the degrees of freedom within is equal to each sample size minus 1. Now notice here you can have different samples with different sample sizes. And so this is how the structural model handles unequal ends better. So here we take each sample size, subtract 1 from it, then add all those together for however many groups you have, and that's the degrees of freedom within. So the estimate of the population variance is equal to the variance between plus the variance within. And now our F statistic, remember the old F statistic, is now going to be represented as a ratio of the variance between to the variance within. Now remember before, if the between variance was high, that means the groups are far apart, because the between variance is calculated by subtracting the sample mean from the grand mean. And if that number is large, that means that there's some disparity in the means of the groups. Well, if the variance within each group is small, then that'll result in a higher F score. But also if there's a big dispersion across the groups with relatively little dispersion or variance within the groups, it suggests that they have integrity being far apart. You can see by chance, if you have a lot of disparity within the groups, you can produce mean differences across the groups pretty easily. So by chance that could happen. But if there's low variance within the groups, that means that a between groups difference probably did not occur by chance. It occurred by design. And so you draw an inference based on probability that that F score is high enough, probably did not occur by chance, which we'll get to in a second. Okay, let's deal with effect size in the structural model analysis of variance. Now the effect size before was basically a ratio of the mean difference to the variance in the simple analysis of variance. Now the structural model, we're going to introduce a new concept. It's still a representation of how far apart the sample means are, but it's a new term. It's a new way of framing it. And as we get further and further into analysis of variance, you'll see how this makes more and more sense. The effect size in this model is R squared. And R squared is defined as the proportion of variance accounted for. It's also called eta squared, or the correlation ratio. It's the proportion of the total variation of scores from the grand mean that's accounted for by the variation between the means of the groups. Now remember, the total variation is composed of deviation of individual scores from the sample means and then deviations of the sample means from the grand mean. Well, the deviation of the sample means from the grand mean of how far apart the means are, the sample means are. So if that's large relative to the total variability that's in the sample, that indicates a large effect size and indicates that the means are far apart from each other. And this is going to be a measure of that. And you take r squared, it equals the sum of squares between. Remember, this is the variance. Sum of squares between is the variability associated with the differences between the sample means divided by the sum of squares total, which is all the variance that's in the study. So it's a ratio of the amount of variability attributed to the differences between the means. And it's calibrated. These are just conventions for size designations. There's no definite terminology that applies to them. But here we see a small effect is 0.01 for r squared, a medium effect is 0.06, and a large effect is 0.14. So just keep those as representations of what the conventions are, what people generally expect to designate as a small, medium, or large effect size. And now we're going to compute this for the birth order study, the one we just did with the spreadsheet. Okay, so now we go back to the spreadsheet, and we're going to do a simple calculation for effect size. Well, if you look at the spreadsheet, you see the sum of squares between is 24.17. The sum of squares within is 34.75. That means the sum of squares total is approximately 59. So you take the sum of squares between, which is 24.1, divide that by 59, and you get approximately 0.4. So the effect size for this little study is 0.4. So that's what the r squared is for this one. All right, now we're going to deal with the issue of power in the structural model. Now remember, power is the probability of finding an effect when it's actually present. So when you actually have an effect, a difference between the means, it's the probability of finding that effect when it's present. Now you can imagine that small effects are harder to find than large, and the more subjects you have, the better chance you're going to find an effect, no matter if it's small or large. But particularly small effects are easier to find when you have more subjects. And you can see that here. If you have the sample sizes here for the three groups of 10, 20, 30, 40, 50, and so on, you can see the probability goes up as these sample sizes go up. So for the small effect, the probability is quite low of finding that effect if you only have 10 subjects. If you have 50 subjects, it actually is not that much higher, but it is much higher than if you have a sample of 10. If you have a large effect, though, and you have just 30 subjects, then you have a pretty good chance of finding it. You have a 93% chance. The probability is quite high of finding a large effect with a relatively small sample. And actually, if you just have a sample size of 20 with a large effect, you have a pretty good chance of finding that effect when it's there. So here you see the relationship between sample size for each group and small, medium, and large effect sizes, and your probability of finding those effects when they're really present.